Welcome, fifth graders, to the Dallas Independent School District STEM Environmental Education Center. I'd like to give a special welcome to three schools who are with us this morning. We have fifth graders from LP Cowart, HI Holland Prep, and Clara Oliver with us this morning. We wish you could be here in person, but since you can't be, we're going to do our best to make you feel like you're here during a virtual field trip experience this morning. If you are watching this and have not registered for this field trip yet, you can still do that by going to www.tiny.cc/3-5 registration so that you can get yourself or your class registered for this field trip. We just use that information for our attendance purposes. And today's virtual field trip is going to be all about physical properties of matter. During this virtual field trip, students will classify matter based on measurable, testable, and observable physical properties. Students will also observe that some mixtures maintain physical properties of their ingredients and that changes can occur in the physical properties of the ingredients of solutions. So we're going to start things off this morning by exploring relative density with Mr. Monroe. Next, we're going to explore all three states of matter with Mr. Dominguez. Third, we're going to explore mixtures with Mr. Mirez. And last but not least, we're going to explore solutions with Ms. Schramm. While we're doing all of that, you can ask us questions. We encourage you to ask questions. Since this is a virtual field trip, the way you do that is you go to www.tiny.cc/question-answer to fill out a super short form to submit any question you have related to physical properties of matter. You can ask as many questions as you like, and we will do our best to answer all of them in the time that we have with you this morning. So let me stop sharing my screen here and turn things over to Mr. Monroe, who's going to get us started off with relative density. You're muted.
Again, good morning, students. My name is Mr. Monroe, and we're going to be looking into density. And we're also going to be looking into relative density, that property of most matters that we always like to compare their weight, but there's more than just the heaviness. And we're going to learn a little bit more about how that all comes together to come up with the answer of density. Now, listen. Density is the measure of compactness of a material. Well, that's another big word, compactness. So what does that really mean? Well, we know that anything that is made up of matter is made up of the building blocks of matter that we call atoms. So when we talk about compactness, we're talking about how tightly the atoms that make up that matter are packed together. And if they're packed real tight, that means higher the density. Now, listen, students, while I go through my presentation with you, I want you to be thinking about two questions. The answer to those two questions, which I'm going to be giving you during my presentation. Now, your teacher may ask you those questions later on, so please pay attention to what is happening, okay? Now, getting back to compactness. You heard me say that means how close the atoms or molecules that make up the atom are to each other. It's more than heaviness. Density includes even how much space the object may take up. All substances have density, including liquids, solids, and gases. Anything that is made up of matter, guess what? It has some density. Now, density is also recognized as the amount of matter per unit volume. Mass of the density usually is expressed in grams. Volume usually expressed in centimeters cubed or milliliters, etc. You know, ice is less dense than water, which is why lakes, ponds have a thin layer of ice covering them in the winter, with the water existing underneath. You know, various rocks, woods, metals have characteristics of density specific to that substance. Now, when we talk about relative density, we're actually talking about the ratio of density of two materials. reference, for example, the water that I have here in the tank, anything less than water, less density than water, is going to float. We're going to be using water as a reference today, and then we're going to be comparing the density of other objects as compared to the water's density. And so that is a descriptive of what relative density means. We're comparing one at a specific standard with the others that we want to test. So we're going to get started. You know, one of the things out here at the Environmental Center I've often been curious about is we were taking a hike in the woods. I wish you guys were here. You would hear me talking about a lot of the trees and plants that make up that ecosystem, the Post Oak Preserve. And I know that some of those plants and trees are actually native or indigenous to that area. But I've often wondered how some of the plants eventually got started there. And we know that happens through some type of seed dispersal. And so when we talk about seed dispersal, that's how seeds are spread around. There are several ways that that can happen: by animals, and even by water, and by wind. So I'm going to be running some tests on some seeds to see if they, because of their density, was able to be moved around by water. Now, objects that float, we say that they are buoyant. Buoyancy is the ability for matter to float. Now, if they don't have any buoyancy, guess what happens to them? They begin to sink. Now, the questions that I'm going to be referring to you to be able to answer is the fact is, what is density and what does high density mean? So hopefully by the end of this presentation, you'll have an understanding and be able to answer those two questions. I'm going to start out by using a very common seed. It's called a pecan. And I'm going to drop this pecan into the water to see if it's buoyant. You know, if we were, again, visiting the Post Oak Preserve, you would notice that there are several native pecan trees that are in the woods there. So more likely, or most likely, animals probably move those pecan seeds in there, because we know that squirrels will bury their seeds and maybe forget that they buried them, you know, storing them up for the winter. And if conditions are just right, that pecan will grow a tree. Let's see if the pecan has any buoyancy to it. Sure enough, there it is, it's floating. So water could have very well moved some pecans into the Post Oak area. And if conditions were just right, guess what we would get? A young pecan tree probably growing into an adult pecan tree. There are a lot of oak trees in the Post Oak Preserve. And we know that oak trees, they produce a seed called an acorn. It looks just like this, okay? Now, let's see if it has any buoyancy. It does have buoyancy. Okay, so that very well could have happened to bring some of the oak trees that we have. And then I have another seed that comes from a weed or a plant, and it's called a cucumber. It's spiky. And I know that animals could have moved this around, simply animals that have fur covering their bodies. This gets caught up in the fur and then drops off somewhere. Conditions get just right and grow that weed that produces these as seeds. So let's see. It has buoyancy. So seeds, most seeds do have, these seeds that we tested today, they do have buoyancy. So water played a big role in moving them because of the density. Now, in measuring the density of water on a scale, density has a rating of 1.00. I want you to remember that. That is a specific condition that we can use to test other objects against, relative density. Now, out here also at the Environmental Ed Center, we have some earth science programs that we do, and a lot of those programs deal with rocks. And we know that rocks are made out of minerals. And the minerals that make up rocks can be kind of like a metal. You'll learn a little bit later about that later on. And some of them may be of other sorts. But again, it goes back to that compactness of the atoms that make up that matter. So I have a rock here, and let's see if there's any buoyancy with it. Nope, went straight to the bottom. How about this rock? Went straight to the bottom. Boy, those were some small rocks. Now I've got a bigger rock here, and I call this my magic rock. It's a rock that we call, or this kind of rock is called pumice, and I'm going to drop it in. Wow, that's why I call it a magic rock. How many of you have ever heard of a rock that floats? Probably most of you, you've learned that in your lower grades. But this pumice, because of the compactness, meaning that the atoms that are making up the minerals in this rock are spread far apart, they're not tightly packed, guess what? The density is less than water. So that means that it has high density, okay? So it's floating. Anything with a higher rating than 1.00, that's high density, that means it's going to float in water. You know, there is a very valuable mineral called gold. And if we look at the scale, gold has a rating of 19.3, and that's pretty heavy. So what do you think if you put some gold in water? What would happen? It would sink because of its density. Cooking oil has a rating of 0.91. What do you think is going to happen to it? Well, to help you understand that, I have a little cooking oil right here. I put a little food coloring in it so we could see the difference between it and water. And I'm going to pour a little bit in this beaker, and we're going to see what happens. Just a little bit. Well, the color didn't go, did it? I've got to stir that up again. But I can tell you what happened. We can see, where is the oil? Did it sink or did it have some buoyancy? It is floating. So there again, remember, water, pure water, is 1.00, and cooking oil is what? 0.91. So cooking oil is less dense than water. So hopefully I've been able to help you understand what relative density is. And guys, listen, my time is up, so I'm going to turn it back over to Mr. Broughton. So if any of you have any questions, I bet he can answer those for you. You guys have a good day.
Thank you, Mr. Monroe. The question that came in was, is there a liquid that is more dense than water? And yes, there is. It is pretty easy to find out which liquids are on the internet, so I'll let you find out for yourselves. But just as a clue, yes, there are liquids that are more dense than water. All right, now we're going to explore the states of matter with Mr. Dominguez.
Hey guys, it's Mr. Dominguez with the EEC, and I am here with a very special guest. I'm here with Bernie the cat. And me and Bernie had a question for you guys. We wanted to ask you what you guys think that Bernie, this can of soda, this plastic bottle of water, this glass test tube, and this Sharpie have in common. So I'm going to give you guys a few seconds to think about it. Pause the video if you have to, and let me know your guesses. So, if you guess that Bernie, this troublemaker, and those inanimate objects are made of matter, then you'd be 100% correct. Now, everything around us in this known universe is made of matter. Now, that includes things you can't see, like air, some other gases like helium, your laptops, everything around you is made of matter. Now in this portion of your virtual field trip, we are going to talk about those states of matter, some of their physical properties, and lastly, we're going to talk about how heating and cooling affects those states of matter. So let's talk about solids first. Now, there's a couple of things that I want you guys to know about solids. Now, solids have a fixed shape and volume. Okay, so these ice cubes are in this shape, and even though you can see some of the ice cube already melting, if this was in the freezer, it would retain this shape. Okay, so, and this volume as well. Now, their particles are closely packed. So what does that mean? So if you were to look under a microscope, their particles, that matter that we were talking about, would look a little bit like this. It would be very tightly packed. Now, these particles are still vibrating, but not enough to where they can flow. Okay, solids are rigid and they cannot be compressed easily. So what does that mean? So if I were to squeeze this, ice cube, it would take a lot for me to change its shape, okay? They cannot be compressed very easily. Now, as you can see, some of that solid already started becoming a liquid, and we'll discuss why in a moment. Let's move on to liquids. All right, so next up we have liquids. Now, liquids are different than solids because one, they have no definite shape. They take the shape of whatever container they are in. Now, liquids are also not rigid. They have no fixed shape, but they do have a fixed volume. Now, regarding the particles of a liquid, you might have guessed that they are a little bit further apart. They are more free to flow. So, hypothetically, if you were able to see the water particles, the matter that makes up this liquid, they would probably look a little bit more further apart than the solid I just drew. Now, this is of course not a model of an actual particle of hydrogen and oxygen, but this is to demonstrate that the particles would be a little bit further apart and more free to flow, just like water. And lastly, we have gases. Now, gases do not have a fixed volume or shape, and most gases you cannot see. So all around you is water vapor, things like oxygen and nitrogen, and you can't really see them. However, if you were to actually be able to see these gas particles, you would see that they are much further apart than both liquids and solids, and they would be scattered more randomly like so. Can you guys think of any examples of gases? So my next question to you guys is pretty simple. How do you guys think we go from a solid to a liquid to a gas? So go ahead and pause the video, and maybe the ice cube melting in my hand will give you a clue. So if you guys guessed that it had to do with my body's temperature, then you guys would be 100% correct. My body's heat was transferring over to the solid matter or the ice cube, and it began melting. Now, you can actually try this at home with a very simple experiment. Now, you could definitely just hold an ice cube and watch it melt, but I actually also want the matter to heat up enough to become a gas. Now, what we're gonna do, and with your parents' permission, you could try this at home. All you need is some ice cubes and a microwave safe container. So the first thing I'm going to do is take this metal thermometer away from my microwave because you're never supposed to put any metal inside the microwave. And I'm going to grab my microwave safe container along with some ice cubes, and I'm going to put my solids into the microwave. And I think I am going to set my microwave for about a minute and see what happens. So what you should have witnessed is a solid being heated up to a point where it became a liquid, and then, as you can see, a gas. Now, before you remove your microwave safe container from your microwave, please either wear protective gloves, some oven gloves, or have your parents remove this very hot container from the microwave so you don't burn yourself. So now that we've seen how we go from a solid to a liquid and then to a gas simply by heating, how do we go backwards? So how do we go from a gas to a liquid and then back to a solid? Well, if we heated the matter to go from a solid to a liquid and then to a gas, then you guessed it. All we have to do to go from a gas and then to a liquid and then back to a solid is to cool the matter down. Now, it's a little bit harder to show, but I'm sure that you've actually experienced that process happening through the process of condensation. Now, what is condensation? So condensation is what happens when a gas cools down and returns to its liquid form. Now, imagine this. Imagine that you have a very cold soda, can of soda, and you're outside in this very, very hot Texas weather. What begins to happen? So it kind of seems like the can begins to sweat, but that's actually not what's happening. What's happening is the water vapor around this can, which is very cold, it begins to cool down. So you start seeing water droplets. So the water vapor that is coming into contact with a very cold can is returning to its liquid form. And if we were to take that liquid and gather it, let's say maybe in a container, we could actually put it in the freezer and cool it down some more, so much so that we could get the solid form of water, which you guys know, of course, is ice, solid ice. I hope you guys enjoyed this portion of your field trip. You guys have a wonderful day, and I can't wait to see you guys next time.
Thank you, Mr. Dominguez. Two questions came in. One is, can we ever see a solid go straight to a gas? And yes, you can. You may have seen dry ice, which is a solid form of carbon dioxide. And when you heat that up, like just at room temperature, it does not actually melt. It turns straight from a solid to a gas, and that is called sublimation. And the other question is there a fourth state of matter? And yes, there is. It is called plasma, which is a superheated gas, and you would be able to find that on the sun. All right, now we're going to explore mixtures with Ms. Ramirez.
Hello, my name is Ms. Ramirez, and we'll be talking about mixtures. So to begin with, I have some very common mixtures that we use here at the Environmental Center. The first is this mixture, and it is a bird seed mixture. So see if you can make out the different components of this mixture. And I, for one, see some peanuts, some sunflower seeds, there's some safflower seeds, and there's some even dehydrated dead mealworms. And to show you what I mean by a mealworm, I have some live mealworms in this container. They are simply a larva form of a beetle. Now these, of course, are live, but in that bird mixture, they were already dead. And I have another mixture that we use a lot here on the farm. This is a chicken or a poultry feed, and it has corn and sunflower seeds, some more dead or freeze-dried insects, and then some oats and other things as well. So I have an animal friend that enjoys eating these mixtures. So I'll give you some clues to who it is, and then I'll let you guys guess while I go pull her out. This animal friend is warm-blooded. She lays eggs that many of you guys probably eat. She is covered in feathers. She's an omnivore. And of course, she loves to eat a variety of mixtures. So go ahead and make your guess as to who this animal is, and then I'll go pull her out for y'all. And if y'all have visited us before or seen our videos, you've probably met Pepper the chicken. So this is Pepper the blue silky chicken. She gets that name because she has that bright blue patch of skin by her ears, and the name Silky because if you guys were to pet her, she feels super soft like silk. Now I mentioned she was an omnivore. She loves eating seed mixtures, but she also eats meat as well. So she will be eating things like the bugs, maybe some tiny little snakes and other things like that. So we're gonna go ahead and put Pepper Chicken up and we'll start off with our presentation. So also be thinking about what are some mixtures that you guys enjoy eating as well. So let me start that presentation, and I have a couple of essential questions for y'all. So hopefully by the end of this presentation, you'll be able to answer these two questions. The first is, what is the definition of a mixture? And the second is, give at least 2 examples of tools that can be used to separate a mixture. And here on the right, you see one of my favorite mixtures that I love to eat, and that's a poke bowl. And it's actually Hawaiian, and it means chopped or cut or sliced into pieces. And I usually like to eat my bowls with crab and chicken and a nice little mixture of some vegetables as well. So again, think about those mixtures that you enjoy eating. Now, we said mixtures a lot. So what is a mixture? Super simple. A mixture is just a combination of 2 or more substances that keep their individual identities. It's important to note that neither substance in a mixture has become something new. They keep those identities, and for the most part, most mixtures can be separated fairly easily. So I have a little video of some common mixtures that we have here at the Environmental Center. The first is one of our previous cats. Her name was Stripey. She's eating a mixture of different colored cat foods. I have my 2 rabbits. We have Stuart and Bella. They're eating a salad mixture. I can easily make out those individual components of that mixture, and for the most part, I can easily separate it out if I wanted to. We also see Pepper the chicken again eating her seed mixture along with some fruits and veggies mixed in there as well. We have some box turtles eating their salad mixture. So we see the okra, the apples, the lettuce, the carrots. Again, we can easily separate that mixture and we can clearly identify the components of that mixture. Now, here's my challenge question for y'all. How can I separate this mixture of paper clips, pebbles, sand, and tree bark? And teachers, feel free to pause the video to allow time for students to create their plan on how they would separate this material without actually using their hands to separate each individual piece. So what are some science tools that you can use to separate this mixture? And also take advantage of those physical properties of each of those components. So again, feel free to pause the video to allow students time to discuss, but I'm gonna go ahead and jump right into it. Now I decided to use some science tools. I used a magnet, a sieve, and a container of water. So using that clue, how could you use those items to separate the mixture? So the first thing I said was, how can we separate the paper clips from the other materials? So what physical property of the paper clips can we use to our advantage? And I used a magnet. So we're taking advantage of magnetism here. Because the paper clips are magnetic, I'm able to remove them using the magnet. After removing all of those paper clips, I now only have the sand, the rocks, and the bark left. So now, given those few remaining items, think about how can I separate the smaller sand from the other materials? So what physical property can I now take advantage of, and what tool do you think I can use? So because I know the sand is much smaller than the rest of the stuff in the mixture, I decided to use a sieve or a screen. You can also use like a piece of mesh. And I'm going to separate or sort those materials by size. So we know the sand is the smallest, so it's going to fall right through that mesh screen and leave all of the big stuff at the top. So I'm taking advantage of the physical property of size. You guys probably use sieves or colanders maybe at home, especially when you're cooking. I know I cook pasta a lot, and I use that to drain my pasta from my water. You probably hear my dogs whining in the background. Now all I have left are my bigger stuff, my rocks, and the tree bark. So what physical property can I take advantage of next? So we heard about density with Mr. Monroe. We're going to use the ability to sink or float. So we know that heavier stuff, the rocks, are going to sink, and the lighter stuff, that bark, is going to float. So now we have successfully separated all of our mixture using some science tools. So our next thing is a scavenger hunt challenge for y'all. I would like for you guys to find 5 examples of mixtures at home or school and explain why each is a mixture. So think about some of these questions I have here on my chart. So we have a saltwater solution. Think about, can this solution be a mixture, and explain? And also look at these cool lava lamps. Can a lava lamp or liquids be a mixture as well? So I'm going to go ahead and stop my screen share, and really quick, I have this to show you guys. You can do this super simple. At home, it's just water that's been colored with food dye, and I have some cooking oil. If you put these together, is that a mixture? Why or why not? And also think, how can you separate it? So that's all I have for you guys on mixtures. We're going to give it back to Mr. Broughton to answer any questions.
Thank you, Mr. Ramirez. The question that came in was is slime a mixture or a solution? And slime is a special type of homogeneous mixture, but it's what it's called is a colloid. Really, it's not a mixture like what you saw Mrs. Ramirez separating with different tools. All right, now we're going to explore solutions with Ms. Schramm.
Good morning, everybody. All right, so we are going to be talking about solutions. And it really ties in nicely with what Ms. Ramirez was teaching us about mixtures. Okay, so you will be able to identify changes that occur in physical properties of the ingredients in solutions. But first, we've got a little bit of vocabulary to go over. So for mixtures, just like you heard from Ms. Ramirez, is 2 or more substances combined that maintain physical properties and are easily separated. Now, solutions are 2 or more substances combined that do not maintain their physical properties. They disperse evenly and they are not easily separated. So with solutions, we have the solvent, the receiving substance, and the most common solvent we'll see is water. The solute is the solid, liquid, or gas that mixes into the solvent. So that's the smaller component. And then the word dissolve, it seems to disappear. So the solute seems to disappear because it distributes evenly or disperses evenly. So we'll see some examples of that in a minute. Okay, so you can make solutions with gases and liquids. And here are some examples. So when you put oxygen into water, the solution becomes dissolved oxygen. So it has a picture of that little goldfish in his tank, and he's got a little aeration stone or a little bubbler, and that distributes the oxygen into the water so that he is able to breathe it in through his gills. When you put carbon dioxide in water and a couple flavors, you can end up with soda. So all that carbonation and those bubbles are evenly distributed. So when you take a sip of Coke, you get bubbles in every sip. It's evenly distributed. Then if you take your straw and blow bubbles into milk, you'll make milk bubbles, and that's an example of solution as well. So you can also make solutions with a solid and a liquid. So once again, our solvent is water, and if you add salt, you will end up with, surprise, salt water. So the salt will dissolve into the water, you stir it up, you won't be able to pick out the parts of salt anymore, and it'll be harder to separate. Iced tea, when you add sugar, becomes sweet tea. Same thing as the salt, the sugar will dissolve. You won't be able to see the sugar anymore, and it'll be harder to separate. When you mix Jello mix with boiling water, surprise, that's how you make Jello. Not a sneaky one there. All right, you can also make solutions with two liquids. So when you add chocolate sauce to milk, chocolate milk. When you mix gasoline with corn oil, you can make ethanol, that's fuel for our cars. And when you mix nectar mix, which is like sugar, food coloring, all these things, when you have the nectar mix and mix it with water, you can make hummingbird nectar. I use those out here. I have a bottle of hummingbird nectar concentrate. That means it's really condensed, and I add water to it and makes a lot of hummingbird nectar. So there's some more solutions, and lemonade is a solution with multiple solutes. Can you think of any other solutions with many solutes? So we have water, sugar, lemon juice, and that makes lemonade. Earlier I made a coffee. I put the coffee through the filter with the water. Then I added creamer, then I added sugar. So that is a big solution. I stirred it right up. Okay, so this example is an example of separating solutions. So just like I said earlier, solutions are harder to separate. When you were with Ms. Ramirez, she was easily able to separate using magnets or other physical properties, but solutions are a little more complicated. So here's an example of a salt flat in Puerto Rico, and this is where they harvest salt. So you can see where the pink water is, that's colored from the salt. And what they do is they have this flat area of land, and they let water in from the ocean. Of course, that water is salt water. And then they block it off. So it's very hot, it's very sunny. So the salt water sits in this area for a very long time. The sun heats it up, and guess what happens to all that water? It evaporates. So the process of turning a liquid into a vapor. So all that water that was from the salt water evaporates, and what's left? Salt. Then they're able to harvest the salt. Okay, so remember that, because I have a challenge for you. So teachers, this would be an awesome experiment or STEM challenge for your classroom. So if you like to pause and not get the answers, then go ahead. Otherwise, I'm gonna go right into it. So what could you, let me see. What could you use? How could you use what you know about mixtures and solutions to separate salt and sand? Okay, so we have sand, salt, and a coffee filter, water, and a rubber band. Those are the only materials that you'll need. So, separating solutions. So at this point, it is a mixture right here. I've combined the salt and the sand. So this is where the challenge begins. You have a mixture of salt and sand. So the first step into separating the salt and sand would be to add water and stir. This creates a solution with the water and the salt. They combine, but sand does not dissolve in water. So the sand is left at the bottom. So how do you remove the sand next? You filter out the sand using that coffee filter, and the salt water will go right through. The sand will be trapped in the filter, and you let it dry. Then you boil the saltwater solution, just like those salt flats. The water will evaporate, and you will be left with the salt. Once the water has evaporated and sand has dried, you will collect, and you will be back to where you started with sand and salt and a little bit of a mess. So my challenge that I'm going to leave you with is just kind of a thinking question. So is it a solution or a mixture? So on the left, we have Kool-Aid is a solution of water, sugar, and food coloring. Then what happens when you add ice? Is that a mixture or a solution? And then once you've answered that, I want you to think, what about once the ice melts? Is that a mixture or is that a solution? All right, so I'm going to leave you with those questions. If you have questions, I'm going to send you back to Mr. Broughton.
Thank you, Ms. Schramm. The question that came in was, is air a mixture or a solution? And I've read quite a few different books and articles about that question, and some say that air is a solution and some say that air is a mixture, but most say that it's a mixture, which I agree with. If you think about air, it's a mixture of oxygen and carbon dioxide and nitrogen and water vapor, but no one substance is dissolved in the other. And your lungs act like a separator of that. When you breathe in, your lungs separate the oxygen from the rest of the air, so your body can use it. So I think air is a mixture. I'm going to share my screen here to do a quick recap of what we did today. So again, this virtual field trip was all about physical properties of matter. So we were able to classify matter based on measurable, testable, and observable physical properties. Students observed that some mixtures maintain the physical properties of their ingredients, and that changes can occur in the physical properties of the ingredients of solutions. So we started things off today by exploring relative density with Mr. Monroe. Next, we explored all three states of matter and how to change states of matter by adding or taking away heat with Mr. Dominguez. Third, we explored mixtures and how to separate mixtures using different tools with Mr. Mirez. And we just saw Ms. Schramm show us all about solutions and how you can use the evaporation to separate salt or sugar from a water, like a sugar water or salt water solution. Thank you so much for joining us this morning. We appreciate you taking the time to learn about physical properties of matter with us. We hope you enjoyed this virtual field trip, and you can let us know whether you did or not by going to www.tiny.cc/3-5 feedback and filling out a short feedback form for us. We use that information to improve what we do here with our virtual field trips. Have a great rest of your day, and we hope to see you again in about 3 weeks for our next virtual field trip for fifth graders. Goodbye.